entanglement and fixed dynamics.
Thank you very much for the invitation and for organizing the workshop. The talk today is divided into two parts. In the first one, I'm focusing on quantum space, and the first part is based on work of a few years ago with Goffredo Kirko and Daniele Lidi. The second part is instead a very recent work with Matteo, Bruno, Fabio Mele and Carlo Rovelli about quantum space-time, the dynamics of the quantum space I'm going to talk about in the first part. So the second part is taking the limits of the structures of the first part, and so looking at the dynamics of space-time. Okay, so let's start from the basics. So in quantum gravity, the main question is what space and time look like at the Planck scale. Now, there are several approaches to quantum gravity, as you know. But so for today, the structure I'm going to talk about comes from very basic ingredients. So just take general relativity and consider canonical quantization. And this is these are the basics of simplicial gravity approaches, like quantum gravity, field theories. So the picture that comes out from these two ingredients is a space which is granular, which is made of quantum entities, in a way that we are going to make precise in the following. I will also adopt a quantum field theory perspective on this. So there is a field theory formulation of approaches like loop quantum gravity, in which you look at these fundamental entities as sort of particles of a field theory. And the space is built up from these entities by gluing them together. And the gluing means entangling the degrees of freedom of these quantum entities. So we are going to see this in a precise way. I will also briefly talk about the holographic properties of quantum space. So we can ask how the information in the bulk and the boundary are related. And so this is the subject of the first part of the talk. And then when we can ask, so what is the dynamics of this quantum space? Now, for the dynamics, so before we talked about quantum space, then we need to consider sort of histories of this structure. So space-time regions, not just space regions. And we are going to see that these histories in these field theory perspectives are like Feynman diagrams in groups. But these quantum amplitudes, they are just an approximation of the full amplitudes. So we need to take, to get the full dynamics, we need to take a continuum limit of these structures. And we are going to see that the physics that emerges in this process depends on how we take the continuum limit. So this is the subject of the second part of the talk. So I have taken out almost all the mathematical details, but if you are interested, ask me and interrupt me anytime and I will comment on them. Okay, so let's start from scratch. Like if you want to define quantum space, where do you start from? So let's consider a building block of space, the simplest one you can have, a tetrahedron. How you describe the geometry of a tetrahedron? Well, you can give me the angles, the lengths of the edges, but you can also just give me 4 vectors, one normal to each face of the tetrahedron, such that the length of the vector is equal to the area of the face. Now, this is enough to describe the geometry of the tetrahedron. actually almost enough, because there is an additional condition, which is the closure constraint, which means that these four vectors need to sum to 0. You can understand this from various perspectives. One is that the geometry is invariant under rotations. No? So it doesn't matter how I orient the tetrahedron, so these four vectors must be invariant under rotations. Penrose had a very intuitive way of thinking about this. Like if I have this tetrahedron and I put it into water and I squeeze the water, the tetrahedron doesn't move. Why? Because the pressure on the different faces compensate themselves. So I have these four vectors. I have the geometry of my tetrahedron. Now these four vectors, to add some mathematical structure, these four vectors are elements of the rotation algebra, SU3. But the algebra of SU3 is the same as the algebra of SU2. So we are going to use SU2 instead, the Lie group SU2. It's not important that if you're not familiar with that, that doesn't matter, but we are going to see this rotation group again and again, because it's the group that encodes this geometric data. So again, think of it as the group of rotations. So this is the classical geometry. I want the quantum geometry. So I need to quantize the phase space of geometries of this tetrahedron. So my vectors, they become angular momentum operators. So these angular momentum operators, they will have eigenvalues, which is the spin, J, and the magnetic number, M. So here I put a dual picture of the tetrahedron, because usually instead of using the tetrahedron, we use vertices, one at the back of each tetrahedron, and four links, one dual to each face. So in these simplicial approaches to quantum gravity, we rely on these graph structures instead of the triangulation, the simplicial structure of the tetrahedron. So now my quantum tetrahedron is this object with four spins, one for each link. And when you canonically quantize gravity and do all the mathematical machinery properly, what you find is that these spins are related to the eigenvalues of the area operator. So this is consistent with the idea that we started from vectors whose norm was the area of the face, and now we indeed have these links dual to the faces with some spins, and this spin encodes the area quantum numbers. This is not the full picture, because we still need to impose the closure constraint. The closure constraint means that the four spins attached to the links must be recoupled in a way that is invariant under rotations. Exactly for the same reason we said the classical geometry is independent of the orientation. And when you do this mathematically, you recouple the representation spaces attached to the links, and in this invariant subspace you can take a basis, and this basis is labeled by a quantum number which is called interpoiner. And this interpoiner, again, when you canonically quantize, you see that is related to the eigenvalues of the volume operators. So, to summarize, the quantum geometry of your tetrahedron is described by the four spins attached to the links, which encode the area of the face, and an interpoiner that we attach to the node, which labels the volume, the quantum volume of the tetrahedron. So, the Hilbert space, or if you want the mathematical precise picture, as I said, we need a group of rotations, one for each link, And then the quotient by another group of rotation is the request for invariant angle rotations. So a basic state, as you see, the basis is again the spins, the magnetic numbers, and the interference. Okay, so I have my quantum tetrahedron. I like to look at the dual picture, the vertex, with these quantum numbers. But then I want to construct quantum geometries out of this. So if you consider space, a quantum space, you can cut into pieces. So you have many tetrahedra composing this quantum space. In the dual picture, this is a graph made of vertices, one per tetrahedron. And this graph has some data attached to it, the spins, which label the faces, the areas of the dual faces, and intertwiners, which encode the volume of the tetrahedra attached to the vertices. Now, so the picture so far, again, was the one common to quantum gravity, spin foam, but in particular group field theory. So in group field theory, you adopted a field theory perspectives on this. How can you understand why you want to move to a field theory framework? Well, if you ask about the theory of quantum gravity, so a formalism that we know works very well is the field theory formalism. So you might hope that gravity is described by a proper field theory. But we also know that gravity, a theory of gravity, must be background independent. So you cannot have a field theory on space-time, because that would be a background structure. So you need a field theory on some auxiliary space, some non-dynamical space. And which space you can use? Well, you can use the local symmetry group of the theory. So again, the group of rotations. So group field theory is a field theory defined not on space-time, but on this group of rotations. So mathematically, you have a field, which is a map from 4 copies of the rotation group to complex numbers. And out of the Hilbert space of the tetrahedron, the one we saw before, you construct the Fock space. So you consider the product of many Hilbert spaces for all possible numbers of tetrahedron, and you symmetrize because you want the tetrahedron must be undistinguishable. There would be no reason to attach a label to them, because again, attaching a label to the tetrahedron would be like having a coordinate system on some background structure. So you want a bosonic statistics for this tetrahedron. So in this picture, the tetrahedron is a field excitation, okay? So it's like one particle state. And the collection of many tetrahedra is an n particle state in this Fock space. So again, the field theory is intended as a field theory of space-time, in which space-time is described as a quantum many-body system. Okay, then we can ask how we build up quantum space, quantum geometries out of these quanta, these tetrahedra. And it turns out that gluing them corresponds to entangling the edge degrees of freedom. And you can understand this if you, so let's look at 2 tetrahedra glued together. When I apply a rotation, if they are glued together, they rotate together. So there is no, like the 2 ends which are glued together, they are not invariant. They are invariant under a common rotation of them. And so this is ensured by the fact that there is maximal entanglement between the 2 edges. And in particular, the maximal entangled state in which they are is the single state, which is the state with total angular momentum 0, because again, I want the 2 to rotate together. otherwise one would rotate in one way and the other in a different way. And then you can construct a precise mathematical framework to describe graphs which are dual to quantum geometries, spin networks graph, so these graphs with quantum geometric data attached to them, by taking n particle state in the blue field theory Fock space and then glue together the degrees of freedom corresponding to the edges in a way that you get the combinatorial pattern you desire. So mathematically you can just apply a projector on each couple of edges you want to glue together. So in this picture we see that the connectivity of space is equal to the entanglement pattern of the space part. Okay, then we can ask what are the holographic properties of this quantum space. Well, the first question you might have is why we care about holography. There are many reasons, so I just picked two bodies of motivations. So one is that, well, gravity shows holographic behavior. So one is, as we presented, due to the fact that in gravity on shell the Hamiltonian is a boundary term, and so it seems that there is an algebra on the boundary encoding the physics in the bulk, and so under certain conditions, in certain frameworks, you have a holographic behavior. Then we have black hole entropy, which famously is an area law, not a volume law. Then you can consider a DSFT, which is a conjecture, but which has been proved in many different contexts, and particular contexts. But the other reason you might care about holographic properties is because, again, as we talked about, it's very difficult to construct observables, gauge invariant observables in the bulk. And usually when we have a boundary, we are kind of safe because we can anchor our observables there, because the boundary conditions restrict the diffeomorphisms we want. And so it's easier to define observables at the boundary. So you might ask how much information about the system I can extract from the boundary. So we studied the conditions under which these quantum spatial geometries have holographic properties. So one question you might ask is indeed how much information from the bulk is encoded in the boundary, in the sense, is there isometric map from a preserving the linear product from the bulk to the boundary? The other question is about the so-called Ryuta-Kayanagi formula, which I'm going to explain in a second. So you can look at the boundary, at the entropy of a subregion of the boundary, and ask if this entropy can be computed through a bulk structure. And indeed, I'm going to present this second part, not the first one because of time, but if you're interested, we will get to that. So the Ryuta-Kayanagi formula has been derived in the anti-de Sitter conformal field theory correspondence, and basically it tells you that so if you have bulk and boundary, the area of a region in the boundary, the entropy of a region A in the boundary is given by the area of a surface in the bulk. So again, this formula was derived in the SFT, so in an holographic context, but you can ask something like this holds in for quantum space, for spin networks. And recall that we are using these graphs, these spin networks, to model quantum geometry. So a link in this boundary is actually dual to elementary surface and carries a spin which encodes the quantum of area for that. So with this graph, I'm really representing the region of quantum space. Oh wow, it's very... okay, so the techniques we use for this are tensor network techniques. So basically we consider our spin networks and we attach some random weights to the vertices. Thanks to these techniques, again I won't enter into the details, but they are very useful because with these techniques entropy computations are mapped to partition function of the Ising model. So basically you just need to look at the partition function of an Ising model in which you have little spins attached to nodes and links. And so what we found is that indeed when we have these random weights attached to vertices and very high spins, a spin network satisfies a law which is exactly like the Euclidean area law. And you have bulk corrections due to the bulk entanglement. And something interesting that you also find is that if the bulk entanglement is very high, you can have the emergence of sort of black hole-like regions in the sense that these regions are so highly entangled that the minimal surface that computes the entropy cannot enter them. Okay, so far we talked about space. What about the dynamics? So, for the dynamics, we need to take histories of these geometries. So what does it mean to take histories of geometries where in a context without time, of course, because we have the quantum gravity regime? Well, you can talk about amplitudes. So you have a spatial geometry and you consider that you have initial space, initial state, and then you have a final state, a final quantum geometry, and you can ask what is the transition amplitude between the two. Again, there I'm considering the triangulation and the dual graph. Since I cannot draw space-time regions in 3 dimensions, I use 1 dimension lower. So now I am considering 2-dimensional space, so that space-time regions is pictured as 3-dimensional triangulation. So we have so-called spin forms, which are indeed like histories of these geometries. So now the vertex interaction is a tetrahedron if, again, just because we moved 1 dimension lower. And so I'm going to talk about this in the second part. So these histories are indeed called spin forms. So these are complexes colored by geometric data, because there were geometric data on the space, so they are, they are attached to the faces once we consider a sort of evolution of these structures. And you can attach an amplitude, a quantum amplitude, to these structures. So without entering in the details, the basic idea is that you have some amplitude for each vertex interaction. Then depending on which, like the specific spin form models, depends on how you choose this interaction vertex amplitude. But the framework, the work I'm going to present is independent of the specific model, so it's fully generic. So in the blue field theory approach, these spin forms are considered like Feynman diagrams in the expansion of your partition functions. But we are not going to focus on that. Instead, we are going to focus on the problem that each of these spin form amplitudes is like an approximation of the full amplitudes, because it's the final triangulation of your space-time region. So the question is, how do we recover the full continuum limit, which is where the dynamics actually lives? So there are 2 main questions which guide this story. The first is indeed, so in quantum gravity we don't have a notion of time. So dynamics means think about transition amplitudes. So what is the structure, which structure these transition amplitudes should have? quantum gravity. And the second question is indeed what does it mean to take the limit of these approximated amplitudes? So what you might ask, actually, like a very basic way of thinking about how the theory of quantum gravity should be, like at the very basic, you want to associate a Hilbert space to a spatial geometry, like think of it like a Cauchy surface. So I want a Hilbert space attached to my Cauchy surface, and then to the space-time region, I want an amplitude, indeed like a transition amplitude. In this picture, it would be like a transition amplitude from nothing to something like a Hartle open state. And you want also these amplitudes to compose in a proper way, right? Because like if I think of a process from A to B and from B to C, that I want the process from A to C to be a proper gluing of the two amplitudes. Now, remarkably, there is a mathematical structure which is very, that match these desiderata, which is a topological quantum field theory as axiomatized by Atiyah in the 80s. Very simply, the framework for a topological quantum field theory is a field theory in which the only observables are global ones, topological ones, so you don't have local degrees of freedom. Gravity in 3 dimensions is a topological theory. So in a topological theory axiomatized by Atiyah, you indeed have a boundary, so a spatial region, and you attach a Hilbert space to it, and then to each manifold, so higher dimensional manifold, which has as boundary your surface sigma, you associate an amplitude which is actually a vector in that Hilbert space. And this data must satisfy certain axioms. Very briefly, what you ask is that if you have two disconnected spatial regions, the Hilbert space is the tensor product of the individual Hilbert spaces. The gluing, which is the most important one, that if you want to glue two manifolds together, then you can do that by the inner product of the respective vectors, states attached to the two halves. Then another crucial axiom is the identity, so the cylinder. The cylinder does nothing in a topological quantum field theory. Well, just take like this manifold and attach a cylinder to it, then with a diffeomorphisms you can just deform it to the original shape. So the cylinder in Atiyah's framework is mapped to the identity operator on the Hilbert space. Now, so we want to, as I said, we would like to put gravity in a framework like Atiyah's one, but there are two things that don't work. The first one is that in Atiyah's framework, Hilbert spaces are finite dimensional, but in a theory of quantum gravity, we expect infinitely many local degrees of freedom, so we expect the Hilbert space to be infinite dimensional. The second one is the cylinder that acts as the identity. Now, in Atiyah's framework, the Hilbert space, the one that you might think of as the Hilbert space attached to a Cauchy surface, for example, is already the physical Hilbert space. So you are done, you have all the dynamics there, and so the cylinder does nothing. But in canonical quantum gravity, usually the Hilbert space we attach to a Cauchy surface is the kinematical one, not the physical one. So the cylinder cannot act as the identity, cannot do nothing. We must actually project kinematical Hilbert space to physical Hilbert space. So it must be a projection in a very precise mathematical sense, which is the one of Raypan algebraic quantization, which probably some of you haven't heard about, but so is basically how you want to define that Dirac quantization in a proper way when the constraints of your theory have, for example, a continuous spectrum. So, maybe I don't have time to answer in this, but if you, even in just usual quantum mechanics, the position space, the position operator, it doesn't have normalizable eigenvectors. So eigenvectors of the position operator don't live in that Hilbert space. You need to leave that Hilbert space. So you need some larger structure to consider your physical states. So I'll get back to this if there is time. But so the main idea is that in quantum gravity we want the cylinder to be a projection from kinematical states to physical ones. So we can play a TS game, but at the discrete level. So we can say, okay, we have the spin network I showed in the first part of the talk, which is dual to a triangulation of space, and I attach a Hilbert space, which is the loop quantum gravity group field theory Hilbert space for spin networks. And then I have a bulk triangulation, so the triangulation of a region of space-time, a spin form, and I attach an amplitude to that, an amplitude. And then I can see that at this discrete level there are the same axioms of Atiyah's framework. So in particular also the gluing of triangulations, except one, which is the identity. Why there is no identity? Well, because the triangulation that, so the bulk triangulation that wouldn't change the boundary triangulation would be something like in the picture. You take the triangle, you just extend. But this is not the triangulation of the cylinder, there is no vertex there. So the problem actually is something we expected, because if we had an identity axiom, then we would get in trouble, because as I said, in gravity we don't want the cylinder to do nothing. So we don't want an identity axiom. That must emerge a proper cylinder structure just in the continuum limit. So we need to refine, to go to the continuum limit, we need to refine the triangulation. A very naive way to do it is like just enlarging the number of the tetrahedra, or like discrete building blocks. But this is too naive. We actually found that if you do that, you fall again in a topological quantum field theory. So then you can do something smarter, which is called the subdivisions. So instead, like here, in the naive way, we kept the boundary fixed, we just increased the number of bulk entities. Instead, in this like better notion of refinement, you refine in a like homogeneous way, and you touch both the bulk and the boundary. But there is something very insightful, which is the fact that if you do this refinement, what happens is that when I refine, I also change the boundary, and so the amplitude is not anymore in the same Hilbert space, because every time I refine, I change the boundary Hilbert space, because it's the Hilbert space for a spin network which is finer and finer. So how do I compare these amplitudes? Well, I need to construct a larger Hilbert space in which I can embed all my spin networks. And this is called the inductive limit Hilbert space. So as you can see, I start with a simple graph, I can embed in a finer one, finer and finer, up to this is called the inductive limit Hilbert space. But what happens is that if I assume the limit to fall into this Hilbert space, I again find a theory which is topological. And we don't want that again. So the lesson is that these continuum amplitudes cannot live in this inductive limit Hilbert space, which is actually good, because this Hilbert space doesn't know about the dynamics. I constructed it from spin networks, not from spin forms. Which is why we actually need this larger structure, the framework of refined algebraic quantization, in which my physical states live out of the kinematic Hilbert space. So in particular, we need to weaken the sense in which these amplitudes, so 2 minutes I'm done, in these amplitudes converge. So they don't converge as usual states, they converge as distributions. And so here there is a mathematical machinery. I'm not going into the details, but we can discuss them if you want. So you enlarge the Hilbert space considering the so-called Gelfand triangle. So what happens is that indeed your states, the continuum states, become distributions on your inductive limit Hilbert space, and out of the cylinder you can construct what is called a rigging map, which is what maps kinematical Hilbert space to physical Hilbert space. So the rigging map, so if I start with two kinematic Hilbert states, like phi and psi, then the scalar product between them, the physical scalar product, is defined from the cylinder. So you attach these kinematic states to the cylinder, and it gives you the physical scalar product between them. So this is my last slide. So through the rigging map defined by the cylinder, we can actually construct the physical Hilbert space. As I said, these continuum amplitudes are distributions on it. And what about the gluing? Well, the gluing survives, but in a weaker form, so a sort of convolution, in the sense that I actually take the two kinematic states, and again, these kinematic states are mapped into the physical Hilbert space by the cylinder. This is actually the gluing properties conjectured, because at the mathematical level, we encountered the problem of defining the full continuum limit. So there is a mathematical issue of swapping the sum over kinematic Hilbert space with the continuum limit of the triangulation. But again, this is a mathematical detail. Okay, so let me conclude. So what I showed you is like how to, if you like, how to think about space and its dynamics, space-time, from very basic ingredients. And we have seen that, so if you consider general relativity, you canonically quantize, and you take the field theory perspective, you have quantum space, which emerges from the entanglement of sort of pre-geometric quanta, some quantum entities. And these structures have an holographic behavior. In particular, you can recover the so-called Diotta-Kalimann formula. And about space-time, well, you consider the histories of these structures, the transition amplitudes between this quantum space. And what you see is that if you take the stronger continuum limit, then the theory collapses to a topological theory, and the physical continuum is reached only in a distributional sense, where the cylinder actually works as a rigging map, which gives you the physical scalar product. Okay, thanks for the attention. Sorry for...
Eugenia, this was really, really lovely. What I comments I guess are going to be like just curiosity or clarifications or things that I would like to understand better. So maybe starting from the recovery of space, from entanglement that you have there, something interesting that comes up in this, of course, is that you get all of this holographic behavior, which is quite nice that you can get in these canonical approaches. I was kind of curious how it relates. If you could say more in detail how the kind of holograph that you get here relates to the ADS CFT types of examples that at least I'm personally more familiar with. So both kind of along two lines, one that you discussed in the talk and one that you talked less about. One is that you use basically tensor network techniques to get back the Diotta-Kalimann formula. Tensor network techniques are used in ADS-CFT, but they're usually used in things that resemble more toy models or simplifications. So, like, how is this supposed at some point to relate to like kind of full ADS-CFT, where we stop using kind of these kinds of simplifications, or is this just like just a different approach that recovers some of that behavior, kind of the basic ideas? And another thing is that you mentioned that the types, if I understand correctly, the types of map that you get in this kind of holography are isometries between bulk and boundary. And one interesting kind of piece of development in ADS-CFT is that there is a non-trivial amount of interest in the context of things like entanglement islands for non-isometric maps between bulk and boundary. So can you also get something like that, for example, within the kind of holographic construction that you have here? A different question relates instead the connection between kind of the two main parts of the talk. So one interesting thing that I'm sure people have noticed is that as you move from space to space-time, we kind of almost lose entanglement along the way. So the space portion, of course, recovers space from entanglement, but then when we move to space-time, this connection between entanglement and the structure that we're trying to make emerge kind of gets lost, and we just start talking about amplitudes and how we connect them. And so I was kind of curious about the extent to which the techniques that you discussed in the first part, for example, regarding the recovery of space from entanglement, can be extended to the second part, if at all, so to the recovery of dynamics, and also some of the holographic behavior that you describe again. So you have the Ryuta-Kayanagi formula that helps in the recovery of space, if it can play any role in the recovery of space-time. And then maybe a couple, yes, okay, a couple more things, just to take as much advantage as I can of the fact that I can ask these questions. One thing that I was curious is the extent to which, since you get the Ryuta-Kayanagi formula, you get holography, you have dynamics. Have you tried to apply some of these techniques to things like black hole entropy? The island formula that I mentioned before, for example, if you can recover it inside of this. Another thing that I'm, and two more things that I'm mildly curious about are, one, if you can maybe expand a bit more on the justification for these distributional limits. At the level of how this, of how the dialectic goes here, it's quite clear. Basically, you take this strong limit, you get a result you don't want, and then you weaken it until you get a result that at least approximates something you want. But you mentioned briefly that this is analogous to, for example, how you would treat in a precise way the position operator in quantum mechanics. So if you could just say more on exactly like how we can make sense and understand why this is actually the correct limit to take, apart from it kind of gets us what we want, which is nice, but maybe not a justification. And finally, if this the structure that you get at the end, so this topological quantum field theory-like object that parameterizes spin for amplitudes, can you actually think of it as a deformation, at least, of the topological quantum field theory? So for something like a topological quantum field theory with defects, for example, or something, or is it just like a different thing that just kind of resembles those axioms? Because if you can, one interesting thing, of course, would be, then the question becomes, if you guys have thought about this, to apply some of the techniques of stuff like extended topological quantum field theories to this spin foam construction that you have, that I think at some point in the past, some of the mathematics people that were looking at these spin foams were interested in. So yes, this is, I think, 5 questions. So I've got time, Nick, in the amount of questions, so I think I'm fine. Okay, thank you.
Thank you. So how much time do I have?
We have 5 minutes, so maybe pick 2 or 3 questions.
Okay. Okay, so let me start. So there are many interesting points you mentioned. Maybe I start from the one I'm most excited about, which is the question of Ryuta-Kayanagi at the dynamic level and the connection to the island formula. So it's true, I talked about Ryuta-Kayanagi only for spin networks. And I haven't talked about Ryuta-Kayanagi for like approaches like spin forms, group field theory at the dynamic level because there is no study of that yet. But what I find most interesting is the following. So indeed the island formula for black hole evaporation is like a cousin of the Ryuta-Kayanagi formula. Is actually, so the Ryuta-Kayanagi formula was derived in the Euclidean context. If you move to the Lorentzian context, you add quantum corrections, you get to the island formula. I think one of the big questions is the island formula, how much it depends on ADS-EFT and how much is independent of holography. So there is a work I've done with Shidong, Don Maroff and Jianchen Wang about how to recover Ryuta-Kayanagi in a in a context which doesn't know about ADS-EFT, starting from a few axioms of the path integral. So you can start from a path integral which doesn't know anything about the UV structures, so it's really a complementary picture respect of the one I presented for spin forms. So you just say, okay, the gravitational path integral, what it should be, like a map from boundary conditions to numbers, because you give me initial and final state, I want the number for the amplitude. And you can characterize this path integral from few properties which you would expect for a well-defined path integral in gravity. And you can show that you can actually reconstruct an algebra and compute the Ryuta-Kayanagi formula. Now, this has been done in a very specific context with spatial regions which are disjoint and in the Euclidean, so you still have the problem of moving to the Lorentzian context. Consider regions which are adjacent to each other, because for the evaporating black holes, you want the information out of a region which is a sub-region of the future infinity. So the factorization problem we talked about. But so the hope is to move from this context to the island formula in the sense of deriving it from few properties of the path integral. And then we have the complementary picture of spin forms, group field theories. And one of the interesting points is that that community has a very different view on black hole evaporation, because at least in loop quantum gravity, people do not expect a page curve. So they expect something like a black to white hole transition, or like information that is lost in the decoherence of the microscopic details of space-time. And so comparing, trying to move to some very generic structure, like an axiomatic structure relative to T, would allow to compare these two perspectives, which can teach us something very important about quantum gravity, because ultimately is how do we think about the Bekenstein-Hawking entropy, because the page curve, like you expect a page curve if you think of Bekenstein-Hawking entropy as counting like the degrees of freedom on the horizon, as they were the only degrees of freedom over black holes. While if you think there are more degrees of freedom in the black hole than the one at the horizon, then you do not expect the page curve. So this is about your question of moving Ryuta-Kayanagi to the dynamic level. This hasn't been done in the spin form context. But yeah, and about the application to the black holes, I mean, this is of course, work in progress. Is a very ambitious program, but the hope is to connect. 2 minutes then. I want to comment on space-time corners you mentioned, because this is related to edge modes and relates to what Guy was talking about of cutting regions. And so when I consider, like I talked about quantum space and spin networks, I haven't stressed that, but what I was talking about is a quantum region of space without boundaries. So when the spin network is a full connected graph, there is no boundaries, like closed region. But then you might want to cut this region in two. And indeed, what you can use instead of topological quantum field theories are extended topological quantum field theories. So let me show you a picture. Yeah, so with extended quantum field, topological quantum field theory, what you do, you cut your Cauchy surface sigma in two. And so what happens for the spin networks? Well, it happens that you have some free ends for your legs. And so the magnetic numbers that we saw at the beginning, and then they disappeared because they were all entangled to connect the different regions. Now they appear again when I cut these regions. And so you can think of these degrees of freedom attached to the free ends to indeed like edge modes, and so you need to then, to glue them back together, you need to entangle them. So this is the framework of extended quantum field theory, something we started working about, but it's still work in progress. But yeah, the answer is that you can use extended topological quantum field theories, the theory of categories for the structure of the Hilbert space, and connect to quantum reference frames, edge modes, and so on. And the last comment, you asked about, can I think of quantum gravity as sort of topological field theory? So I would say no. So we use that as framework because it was a very clear picture of having space regions, Hilbert spaces, space-time regions, amplitudes. This data satisfies certain properties, the gluing, the identity, and so on. But then gravity is not topological, so we need to break this structure, and we see that it's important to break it because we don't expect something like the cylinder to do nothing. We don't expect finite-dimensional Hilbert space, so we definitely need to go beyond the topological quantum field theory picture. And we saw that it already breaks at the discrete level, and it breaks even more in the continuum level, where even the gluing doesn't work as in Hilbert's framework.
Thank you very much, Eugenia. It was great to hear this presentation. So I have many questions. I'll just stick to two for the moment. Maybe I'll ask you later. And so I think the first issue I would have is how to interpret physically some of the things that we're talking about of these QG quanta. So first of all, which kind of motivation we have to construct a box space such that we think that these structures are to be taken as bosonic in nature, and whether this is somehow connected to cosmological applications, or whether that's not the case. And I've always asked myself how I should interpret these, the status of angular momentum operators in a setting in which I don't have a spatial-temporal structure. So as long as I construct my objects in this copies of a group, how should I think about the angular momentum in the first place? And then other questions are related more to a very interesting aspect that you mentioned concerning why we want to have orthographic properties, and in particular, what is the role of boundary conditions, because they somehow seems to be constraining the space of allowed diffeomorphism. So I was wondering if you could say a bit more about this.
Okay, sure. So about how to think of these angular momentum operators. So indeed, when we talk about like the quantum tetrahedron, and then we have this idea of quantum space made up of tetrahedra glued to each other, is a bit misleading because of course, as you said, there is no space, there is no time. These concepts emerge in some continuum and classical limit. I only talked about the continuum limit, not the classical one, which is another issue. And so often you read that, we define these entities as pre-geometric because like the data, so we attach some data to them, the one coming from this angular momentum observables, because of the symmetries of the theory, and because in the, at least in the continuum limit, also in the classical limit, we know to relate to the holonomy, the connection, or the structure we have to describe geometry instead of with the metric, with the connection and tetrads and so on. But they are pre-geometric in the sense that it's true that you don't have a geometry at that level, so you don't have a notion of distance, you don't have a notion of metric. So I don't know how what would be the approach of a philosopher, but I think it's really a cartoon, one of the quantum tetrahedron, because in the end we are like just describing quantum entities that we can picture in space and time. So, and about the angular momentum operators, well, so as I said, it comes from the symmetry group of the theory, and actually what is interesting is that Roger Penrose derived the spin networks completely independently of general relativity and canonical quantization. So he just asked what quantum space should look like. I don't know if you're familiar with that, but he just started from directions of space, and he came out with SO2 variables. So there seems to be something very fundamental in the rotation group, but in the end we want to describe geometry in a rotational independent way, because orientation doesn't matter, because it's background independent theory. The symmetry is the Lorentz group, but kind of break it into foliate in some way from space and time, these rotations. So it's like fuzzy geometry that of the tetrahedron is like even the magnetic numbers that tell you how much there is like the projection of the axis of the angular momentum you chose. It's a quantum number, so it fluctuates. So, what the other question was about
what we should care about holographic properties and the fact that on the boundary we may have
right.
constraint mechanism.
Yeah, so the fact is that when we consider so the most important feature, and we need to consider observables which are invariant under diffeomorphisms. And diffeomorphisms usually they die off at the boundary, so we consider invariance under diffeomorphisms in the bulk. And then we fix some boundary conditions. We say, for example, space-time is asymptotically flat. And so you might still have some symmetries at your boundary, but not the diffeomorphisms, or what I call large diffeomorphisms, but they are proper symmetry of the theory, it's not just gauge redundancy. And so the boundary is like an anchor where you can actually give meaning to coordinates, and so you can safely identify the region. And this connects to also your question about why the Fock space, why the bosonic statistics. It's because so if I have some tetrahedra in a background independent context, I cannot distinguish them. I cannot say this is tetrahedron 1, 2, 3, 4. I mean, I can distinguish them just based on their properties. I cannot attach names because it would be like attach coordinates on some background. So you want a bosonic statistic because you want undistinguishability of them. And so you want this quanta to be like bosons. And this relates also to the question of the cosmological application, because it's like in the limit, when you try to connect to cosmology, you have some Bose-Einstein condensate out of these entities which follow bosonic statistics. So it's hardly relevant for the continuum classical limit in a cosmological setting. I'm not an expert on the Bose-Einstein condensate.
Because we should really team dynamic with film statistics. Of course, you would have.
Oh yes,
That's what
but sorry. Okay, yes, of course, but there would be no reason to ask that to tetrahedron to be in the same state, right?
Yeah.
So, and it's because of the geometry interpretation you have in mind that you want to treat them like Bose and frequency.
Thank you.
That's actually. So this was very informative, thank you. I want to understand better, perhaps as a follow-up to Amelia, the relationship between this research program and holography. So one thing that you said, which caught my attention, is that you expect the Hilbert space to be infinite dimensional. And usually when you have holographic entropy, that's actually grounds to treat the Hilbert space as finite dimensional. So I'd appreciate clarification on that. And I'd also appreciate why the holographic properties of this research program don't translate necessarily to holographic black hole entropy, because you said a lot of people in this community don't necessarily view Bekenstein-Hawking entropy as bound on total black hole entropy. It's just horizon entropy. And that's why you don't follow the page curve that people tend to think of, although for the black hole to white hole transition, I would still say that's a page curve. It's just a very delayed page curve. You have more degrees of freedom that can support entanglement for a longer period of time. And it's only after the transition that you get information coming out. So yeah, I would just like to understand better how not being holographic about black hole entropy is compatible with being holographic in the other ways that you're talking about, and why the infinite dimensional Hilbert space.
Okay. So thank you for this clarification on the page curve. Indeed, like talking about no page curve in that context was not like what I really meant is that the Hawking entropy is not thermal. So when I say no page curve, what I actually meant is that when you consider the radiation, the Hawking radiation, and around the page time you see a third over of the curve for like the black to white hole transition. You don't see that, you see that increasing. So, but it's you're of course right that you have a page curve just a later time because information goes out of the white hole. So thanks for clarifying that. So is your concern about the fact that I talked about holographic properties at the kinematic level, and so I expect some holographic properties to survive also at the dynamic level in the
Maybe that's the question I should be asking.
okay.
I just wanted to understand why, I guess, some consequences of holography that I'm used to are actively not being taken on board in your research program, or why you can disentangle them.
Okay, sure. First, a disclaimer that I'm actually not. Okay, so let me just be clear about this. For example, black to white hole transition. So the idea is to be kind of conservative about quantum gravity, and say, okay, I don't want like one of the main reasons is to say I don't want quantum field theory to break down at the page time, because it's a regime is still classical. There is no reason to assume some no locality in the evaporation process. And so the idea for this scenario is that, well, if I assume that Bekenstein-Hawking entropy is not the full, it doesn't count the all the degrees of freedom, then I still have some, I still have some freedom for these additional degrees of freedom to do this transition to the white hole. And so the idea is that, okay, I can find a solution of the Einstein equations for this space-time, the black and white hole space-time, everywhere except for the quantum region where this transition from black to white hole happens. So it's like, okay, in this way I have, now there is no greater quantum field theory, there is unitarity and so on. What I find interesting about this other approach instead, the computations with the path integral, is that, I mean, I don't have an answer on if the island formula really works without the SFT, because many, like you can do the computation with another path integral, but the interpretation is really tied with the SFT. And one of the reasons is because how I interpret the state, like to have a proper state at the boundary, any factorization of the Hilbert space. I mean, all these like subtleties, maybe in holography works well because there is a duality, so I use that. But still, it seems that if you like assume a gravitational path integral and you believe in summing over topologies, you do the you imagine doing this black hole evaporation experiment many times to apply the so-called replica trick and so on. And so it seems that there is actually this turnover of the entropy. So it's not an assumption in that computations, provided that you can actually interpret it without the SFT. There is no assumption to start from that the Dirichlet-Steinhausen entropy is counting just is counting all degrees of freedom. You actually derive this. So I think it's very important to understand that and to what extent it survives without the SFT, because that is like a non-perturbative full picture. While this, I mean, there are. Of course, the black to white hole transition is also, I think, I'm not an expert on that, but I mean, there are issues on how to compute these amplitudes and how to treat the space-time coordinates and so on. So there are, like my hope is to investigate these questions without using the SFT and see to what extent I can derive them from a path integral which satisfies certain properties like the ones I listed there, so that we don't have to start from all of that assumptions. And about the Hilbert space, that is a very interesting question, very much debated. Because if you believe in holography and you have a Cauchy surface with no boundary, you would say the Hilbert space is finally dimensional. So I don't have actually a clear answer to that. But I mean, I wouldn't expect indeed to actually have a trivial Hilbert space if there is no boundary. But is it possibly the problem, because I mean, I still have a lot of observables, right? Even if there is no boundary, there is a lot of physics, of course, going on. And I think it's a problem on how you define, like probably when you consider relational physics, and so you can actually start breaking out the structure into observer and the systems you are observing, then I think you get out all the richness of the Hilbert space you're looking for. So I think it's like, but I'm very happy to discuss about that, because the problem is the Hilbert space attached to like a closed Cauchy surface, one-dimensional or not. It's very much debated. I think the point is how you properly define the observables of your theory.
Yeah, I'm trying to work out whether physical space-time in this picture is discrete. One reason to think it is because you're gluing together these...
Space-time or space?
Space-time, yeah. So you're gluing together these objects that encode information that looks like simplexes, and that starts to look like you're gluing together chunks. But then you said things like the dynamics lives in the continuum limit, the physical information is in the continuum limit, which makes me think that actually that discrete stuff is not really physically relevant. It's all what's happening in the continuum. And so then the physical space-time is not discrete, but I'm just not sure how to think of this.
Okay, so indeed, when we consider, one point is that why the discrete is not enough. Actually, why the discrete space-time is there in the first place is because if I assume quantum space to be granular and I want to consider a transition, what I do is to interpolate between the two boundary triangulations, and so I still get a complex interpolating them. And so the granularity of the space translates into the granularity of space-time once I consider how to fill the gap between two regions, and so consider transition amplitudes. But both the granularity at the quantum space and the granularity at the space-time and the space-time pictures, they are actually approximations in the sense that when I introduce spin networks, a quantum space, I have this picture of quantum space made up of these little tetrahedra. This is like a triangulation of space, so I still want to refine it, and refining it means taking the continuum limit of these structures. And you can, just thinking about gravity, you expect infinitely many local degrees of freedom, and so you can see that it's not enough to have this discrete structure, which is like cutting the number of possible degrees of freedom. So if you start with a manifold, you can consider, which is the loop quantum gravity picture, you start with a manifold, and then you say, okay, let me consider the holonomy on different possible paths inside of this. And this is a first triangulation of space. But then I want to cover the whole manifold, and so I want to consider all possible paths, and so I want to refine, keep refining the graph, because that was like a truncation of the graph. So in this sense, the continuum limit is what should be able to grasp more and more degrees of freedom, because in the end we know that we want to end up with general relativity, hopefully, and with a theory with infinitely many local degrees of freedom.
So the tetrahedra are like physical, or are they just a mathematical trick for producing space-time?
Okay. This is a great question, because the question is how do you think about this emergence? I don't actually, I don't know how to think about, for sure it's something like you mathematically need, because you want the full dynamics to be present. You want to recover the full dynamics, and so you want to take this continuum limit, again, because the free level is cutting the degrees of freedom. Now, if then, in taking this continuum limit, how to think about this sort of phase transition between this granular structure and some continuum structure, that I don't know, the philosophical question that I don't have a good answer for that. I think it depends, for example, even on how many possible phases do you have? You might consider a phase in this emergence of space-time, which is geometric, and then you consider what's called geometrogenesis. And when you can consider phases in which you don't end up with a geometric picture, and so this would change your view on these three geometric entities, right? So they are not just like a truncation of the space-time, the continuous space-time, if out of them I can also recover some structures which are not geometric at all. So no, it's a very interesting philosophical question, but don't have a better answer.
Okay, Baptiste, as a follow-up.
Yeah, no, I had a very similar question about the continuum limit. What's the kind of metaphysical picture in the background? And I had the impression that in a way that the picture is such that the fundamental ontology is not discrete. It's non-spatial temporal, you have some kind of vagueness, infinitely many degrees of freedom, and the kind of tetrahedron is kind of a mathematical projection to try to project order and mitigate the quantum vagueness or something.
Yeah.
So that's kind of picture you have in mind, right?
Yes.
So in a way,
I mean, because as I said, it depends also what you can get out of them, right? If I get something dramatic that all this changes my perspective on these entities.
right. Okay, in a way, we could use the limit for different goals, right? One might be just to recover geometry or something close enough to explain its predictive success, but we may have other reasons related to the fact that we think that the fundamental ontology is continuous or something. And I think, yeah, that geometry could be showing that we exchange.
I mean, it's a question indeed how to think of these entities in a context without space and time, so you can't really.
But it could be in principle, it could be both non-spatial temporal and discrete, right?
Yes, sure.
Or alternatively, it could be both non-spatial temporal and continuous, even the continuity is not to be interpreted in terms of space-time and information, whatever. So it seems there are two possible projects there, right?
Yes.
Right. And you are kind of doing your work based on one possibility.
Right, yes.
He has a very brief last question.
No, I don't.
You don't?
No, I do.
Okay.
I have two questions, but I can talk more later. But I just want to go back to the point that Sachi was making before, because I'm really trying to understand why your intuition would be that quantum gravity tells us that there are infinitely many local degrees of freedom. Because my intuition and what I know from holography and thinking about black hole thermodynamics and entropy would tell me the other way around. But somehow you were inferring the opposite conclusion, and I'm trying to understand why.
I'm thinking about gravitational waves, for example. I would turn the question to you, why you expect infinity? I mean, what? Like,
I mean, if I think about black hole entropy being finite, and a black hole is assigned to a local region space-time, and I think this is coming from entanglement entropy, and I have a max entangled system, then I know the dimensionality over space is going to be actually exponential of that entropy.
now what if there is anything entropy is counting only the degree of freedom on the horizon? That wouldn't be in favor of holography anymore, right? So, I don't know,
Sure, but that
it
question.
depends on what I start from and what are my first, no? So, of course, if you tell me, okay, the Vegas anything entropy is the entropy of the full black hole system, and then the strong hint that there are not really many local degrees of freedom because it's finite, so I don't expect. So I don't know, I think it depends on, which assumption, or let's say, which hints you consider more ways. So I expect, when I say infinitely many local degrees of freedom is also because, indeed, I'm thinking in terms of like just general relativity, and so I would expect. I mean, let me say it like this, I have no strong reasons to think that the Hilbert space for gravitational degrees of freedom should be finite. And I would say this. Like the Hilbert space attached to a Cauchy surface. you would say that it's finite. But the rarity surface, even, sorry, Cauchy surface.
I would be at least maybe agnostic then.
Yeah. So this is why Decaine was worried about let's relax Satir's framework to not stick to k-dimensional Hilbert spaces because there is no strong, maybe the claim is like must be three-dimensional is too strong, but I want to be able to accommodate in three-dimensional. And even if I start just from this like granular structure, the spin networks, I refine. Well, in the end, you expect something like infinitely many degrees of freedom locally because my refinement in the end wants to cover continuously the